See, in the beginning, the first chapter itself, we have seen the different states of matter, the different physical states of matter. We have seen, we have seen that there are three important physical states of matter. And the three important physical states are gas, liquid, and solids. Gas, liquids, and solids. These are the three important states of physical states of matter. Here we are to see the gaseous states. The present chapter will see only the gaseous states. If we take a system, maybe a gaseous system or a liquid system or a solid system, there will be different attractive forces between the molecules. The attractive forces between the molecules, intermolecular force of attraction, that is known as van der Waals forces. The intermolecular force of attraction between the molecules, between the molecules are known as van der Waals forces. Van der Waals, van der Waals, van der Waals, van der Waals. See, van der Waals is the full name. Van der Waals, including S. So van der Waals force of attraction between the molecules. Van der Waals forces. So van der Waals forces do not include the ionic forces or ionic bonds and the covalent forces or covalent bonds. Not included these attractive forces. So the forces other than ionic bonds and covalent bonds, these are the van der Waals forces. So the attractive forces between the molecules in a system, especially in a gaseous system, are known as van der Waals forces. Van der Waals. Van der Waals is the full name. Van der Waals. There are three different types of van der Waals forces. One is called the dispersion force or a London force. Dispersion force. It is also known as the London force. London. That's the name of a person, scientist. The London force. The dispersion force or the London force. Second one, that is a dipole forces. Dipole interaction. Dipole interaction or a dipole forces. Attraction between the dipole interaction. And third one is induced dipole interaction. Induced dipole interaction or dipole induced dipole forces. So these are the three types of van der Waals forces. I repeat, the attractive intermolecular forces between molecules are generally known as van der Waals forces. The van der Waals forces may be classified into dispersion forces or London forces, dipole interaction or dipole forces, and dipole induced dipole forces. Let us see what are these. What are the dispersion forces or London forces? The first one, the dispersion forces, or the London forces. The London forces. What are these? You take, say, for example, an inert gas molecule, a noble gas molecule. Noble gases are monatomic gases. So the molecule of a noble gas is the same as its atom. Normally, the atoms will be having, say, the neutral structure like this. At the center, there is the nucleus. Surrounding the nucleus, there will be electron cloud or electron charge or negatively charged electrons. Electrons are negatively charged, and due to the motion of the electrons, there will be a cloud of a negative charge. A cloud of a negative charge. The cloud of negative charge, we call it as the orbital. The cloud of negative charge is uniform or symmetric. It is symmetric in nature. But during the motion of the molecules, sometimes the molecules will be having, so it will be losing its symmetry. The molecule loses its symmetry, and say it becomes say like this. And so to one end there will be the positive charge, and here there is accumulation of a negative charge. Say the symmetry is lost. In the previous case, the nucleus was at the center of the electron cloud. And so there is a uniform distribution of the negative charge surrounding the nucleus. So there is no charge separation. But there are cases, instances at which the molecule loses its symmetry, and there will be the charge separation in such a way that the nucleus is moving to one end, and the negatively charged electron cloud or the negative charge accumulates on the other side. And due to this, what happens? The symmetry is lost, and here there is formation of the partial negative charge at one end, and here there is a partial positive charge at the other end. If there is charge separation like this, it is dipole. There is a partial charge separation, then it is a dipole. And this dipole is a transient dipole or a temporary, it is a temporary dipole. It is a transient dipole or a temporary dipole. If a temporary dipole is formed like this, temporary dipole or a transient dipole is formed, then the temporary dipole is formed, a transient dipole is formed. There is attraction between the temporary dipoles. See, here we have a temporary dipole. There is another temporary dipole. See, like this. There will be the temporary dipole like this. And there is attraction between the negative and the positive end of the negative end and the positive end of the temporary dipole. And this type of attraction between the temporary dipoles, temporary or transient, momentary, transient dipole, that is called the dispersion forces or the London forces. So the London forces or the dispersion forces is the attractive force between temporary dipoles or transient dipoles. We can see this type of London forces or dispersion forces in, say, noble gases, gases like hydrogen, oxygen, nitrogen, etc. Especially during the liquefaction, there is a formation of temporary dipoles, and there is attraction between the temporary dipoles, and it is called the dispersion force or the London force. Now you come to the dipole-dipole interaction. Dipole-dipole interaction. And this is the attractive force between two permanent dipoles. Permanent dipoles. As you know, a permanent dipole is formed due to the difference in the electronegativities of the combining atoms in the covalent molecules. So, for example, you take a HCl, hydrogen chloride molecule. Here, chlorine is more electronegative than hydrogen. Chlorine is more electronegative than hydrogen. And therefore, the electron pair is shifted towards chlorine, more electronegative atom chlorine, and it gets a partial negative charge, and here there is a partial positive charge. There is a permanent dipole like this in HCl, HF, H2O, NH3, etc. In all these cases, there will be permanent dipole, and that is due to the difference in the electronegativity values of the combining atoms. If there is permanent dipole like this, there will be natural attraction between the permanent dipole, say plus, and here there is minus, and so there is attraction between the permanent dipoles, and it is the dipole-dipole interaction or a dipole-dipole force. So dipole-dipole force or a dipole-dipole interaction is the attractive force between permanent dipoles. The molecule will be a permanent dipole. If it is a permanent dipole, there is always the charge separation. Plus minus charge separation will be there always. And there is attraction between the permanent dipoles, and it is called the dipole-dipole interaction or a dipole-dipole forces. Now you come to another type, and it is the dipole-induced dipole. The dipole-induced dipole force. Induced dipole interaction. The dipole-induced dipole interaction. And this is the attraction between a permanent dipole and an induced dipole. What is the meaning of this? For example, you take ammonia, NH3 molecule. Ammonia molecule. As you know, in ammonia molecule, there is charge separation. There is a charge separation. It is a permanent dipole. Here there is a plus, here there is a minus, minus delta, there is plus, here there is a plus. It's a permanent dipole. Now, when such a molecule approaches a neutral molecule, for example, benzene, due to the negative charge, the other molecule, the neutral molecule, which is not a permanent dipole, it is not a dipole at all, and there is formation of a temporary dipole by the action, by the presence of this permanent dipole. Due to the presence of this permanent dipole, the neutral molecule or a non-polar molecule, it becomes a dipole. So dipole is induced on other molecules. And such a dipole is called an induced dipole. Induced dipole. The dipole nature is induced by the action of, for example, benzene. In benzene, due to the presence of ammonia molecules, a dipole is induced. Charge separation is induced. So benzene becomes a temporary dipole, or it becomes an induced dipole by the action of this permanent dipole. So, and the attraction between a permanent dipole and induced dipole, that is called the dipole-induced dipole interaction. So, in the various systems, for example, a gaseous system, there will be attractive forces between the molecules. Attractive forces between the molecules. And the attractive force between the molecules are called van der Waals forces. Remember that van der Waals forces do not include the ionic bonds or covalent bonds. So the other types of attractive forces, that is excluding ionic bonds and covalent bonds. The other types of attractive forces seen in various systems, and that is called van der Waals forces, like the dispersion force or a London force, dipole-dipole interaction, dipole-induced dipole interaction. As you know, the London force or a dispersion force is the attractive force between temporary dipoles. The molecule is not a dipole at all. That is not a permanent dipole at all. But at some cases, the molecule becomes temporarily, it becomes a dipole due to the the separation of the negative charge, the negative electron charge on one side and the movement of a nucleus to the other side. The symmetry is lost and there is formation of a temporary dipole. And the attraction between two temporary dipoles, that is called the London forces or dispersion forces. And second one, dipole-dipole interaction. Here, the two molecules are permanent dipoles. They are permanent dipoles. And there is attraction between two permanent dipoles, and it's called dipole-dipole forces or dipole-dipole interaction. And third one, dipole-induced dipole forces. Induced dipole forces. By the action of a permanent dipole, a non-polar molecule becomes a temporary dipole. We have two types of molecules. One type of molecules are permanent dipoles. The others are not dipoles at all. But due to the approach of the permanent dipole, the non-polar molecule becomes a temporary dipole. And there is attraction between the permanent dipole and the temporary dipole. And that is called the induced dipole interaction or dipole induced dipole forces. So these are the three types of the van der Waals forces seen between molecules, especially in the case of the gaseous system. When we speak about the gaseous system, we know that only 11 elements are seen in the gaseous system under stay normal conditions, under atmospheric conditions, room temperature conditions. And the 11 gases, the gaseous systems, they are hydrogen, oxygen, nitrogen, then chlorine, fluorine, and the others are noble gases, helium, neon, argon, krypton, xenon, and radon. So these are the 11 gases which are seen normally under room temperature. And all others are either liquids or in the solid state. Only these 11 elements, I repeat, hydrogen, oxygen, nitrogen, fluorine, chlorine. Then the noble gases, helium, neon, argon, krypton, xenon, and radon. And these 11 elements are seen in the gaseous state at room temperature, and the others are in the liquid state, or they are in the gaseous state. Sorry, in the solid state. Okay. Now let us see the various gas laws. In this chapter, We have to see only some gas laws. You must have studied this in physics. The gas laws you might have studied in physics. The various gas laws. Only we have to see the gas laws in this chapter. The first one is the Boyle's law. Boyle, B-O-Y-L-E, Boyle. B-O-Y-L-E, Boyle. The Boyle's law. Boyle's law. Let us take a gaseous system. Here there is a cylinder and there is a piston, cylinder and a piston arrangement. In this, we are taken a gas. So a gas is confined in a cylinder. The variables are, one is volume, the second one is pressure, then third one is temperature, and fourth one is the amount or number of moles. Number of moles. These are the different variables, the different variables that govern a gaseous system. We are taking a gas in a cylinder. You have confined the gas in a cylinder by means of a piston. And the variables are volume of the gas, pressure of the gas, temperature, and the amount, that is number of moles. Amount, number of moles, N. So these are the variables. The gas laws are concerned with the changes in these variables. You keep any two of these variables constants. You keep any of two of these variables constants. And you study the variation of the other two variables, the change in the other two variables. And that is what we are going to see here. In the Boyle's law, we see the relation between pressure and volume. Pressure and volume, the variation of pressure and volume. And what we have to do? We have to keep the mass of the gas a constant. Temperature is also kept a constant. So keep the mass a constant. You take a fixed mass, a fixed mass. So the mass, number of moles, that is kept constant. Now you keep the temperature also a constant. Then you study the variation of pressure and volume. And that is the Boyle's law. So Boyle's law gives the variation of the pressure and volume at a constant temperature if the mass of a gas is kept a constant. And the statement of the law goes like this. At constant temperature, do you remember? At a constant temperature. See, we are keeping the temperature a constant. The pressure of a fixed mass, definite mass, a fixed mass. So mass is fixed. Mass is fixed. Number of moles, that is fixed. Temperature is also fixed. So at constant temperature, the pressure of a fixed mass of a gas is inversely proportional to volume. Inversely proportional to volume. Inversely proportional to volume of the gas. V, volume of the gas. And that is the relation. See, we are keeping temperature a constant and the mass or number of moles of the gas a constant. Now you study the variation of the pressure and volume. And according to Boyle's law, at constant temperature, the pressure of a definite mass, a fixed mass of a gas is inversely proportional. Pressure is inversely proportional to volume. Pressure is inversely proportional to volume. So how can we show this? Pressure is inversely proportional to say volume at a constant T, at a constant temperature. Pressure of a definite mass of a gas is inversely proportional to volume at constant temperature. At constant temperature, the pressure P of a fixed mass of a gas is inversely proportional to its volume V. So the Boyle's law can be written as P proportional to 1 by V. That is inversely proportional. 1 by V. Or you can say V proportional to 1 by P. Both are correct. Okay. And that is the statement of Boyle's law. If it is so, say P is equal to a constant divided by V. Or we can say PV is equal to constant. PV is equal to constant at a constant temperature. PV is a constant at constant temperature. And this is also another form of Boyle's law. This is the mathematical representation of Boyle's law. This is also PV is equal to constant at constant temperature. That is also another mathematical formulation of Boyle's law. You can generalize this equation as, say, P1 V1 is equal to P2 V2 is equal to P3 V3 is equal to etc. etc. These are the pressures and volumes of the gases, pressures and volumes of the gases at the constant temperature. So, according to Boyle's law, the pressure of a definite mass of a gas is inversely proportional to volume. So, P proportional to 1 by V at constant temperature. Or you get PV is equal to constant at a constant temperature. From this relation, at constant temperature, P1 V1 is equal to P2 V2 is equal to P3 V3 is equal to etc. etc. Okay, so these two are the mathematical formulation of the Boyle's law. P proportional to 1 by V at constant T, or PV is equal to constant at a constant T. The equation form, the mathematical form of Boyle's law. We can show the Boyle's law in the form of a graph, the graphical representation, for which we have to plot pressure against volume, pressure against volume at a constant temperature. You can plot pressure against volume at a constant temperature. And that plot is called isotherm. It is called isotherm. Isotherm. Iso means same. Therm is related to temperature. Temperature. And so isotherm, that is a plot or a curve between pressure, a plot of a pressure against volume at a constant temperature, at a constant temperature. That plot is called isotherm. So isotherm is a graph obtained by plotting pressure against volume at constant temperature, or it is a plot of pressure against volume at a constant temperature, and it is called an isotherm. And what will be the nature of the graph obtained? Say the nature of the graph will be like this. Say we are going to plot pressure on the y-axis and the volume on the x-axis, and you plot the pressure against volume at a constant temperature, and you will get a graph like this. And this graph, that is called the isotherm. Isotherm. Isotherm, a plot of or a graph of pressure against volume at constant temperature. That's called the isotherm of the gas. And this is the graphical representation. When pressure increases, volume decreases. We have seen that P proportional to 1 by V, P proportional to 1 by V. So when pressure increases, volume decreases, and the nature of the graph will be like this. And this is the graphical representation of a Boyle's law. And this curve or this graph that is known as the isotherm. If you, if this is the graph at say, temperature T1, then you plot the same at temperature T2. That is another isotherm, another isotherm. See here, T2 is greater than T1. T2 is greater than T1. Anyhow, you just remember this one, this graph. At least this you remember. A plot of pressure against volume at a constant temperature. And that is known as the isotherm. And that is the graphical representation of the Boyle's law. We can plot pressure against 1 by V, pressure against 1 by V. You plot pressure against 1 by V. Then the graph obtained will be, say, like this. This is the nature of the graph obtained. And that is also another graphical representation of a Boyle's law. Another graphical representation of a Boyle's law. If this is for temperature T1, this is for temperature T2, here also T2 is greater than T1. So you remember this one, a graph between pressure and 1 by V. Instead of V, we are plotting 1 by V at constant temperature. And that graph is called, that curve is called the Boyle's law curve. That is another graphical representation of Boyle's law. So this is also Boyle's law. Say, this is our Boyle's law. P proportional to 1 by V. P proportional to 1 by V. So from this relation, when pressure increases, so volume decreases. 1 by V, reciprocal, inversely proportional, and therefore the nature of the graph is like this. If P and V are plotted, instead of P and V, if we plot P against 1 by V, P and 1 by V, then you will get a straight line passing through the origin. That is also the graphical representation of a Boyle's law. From the Boyle's law, we have studied this. PV is equal to constant at a constant temperature. And therefore, if we plot PV against pressure or volume at constant temperature, you will get a straight line parallel to the pressure axis or the volume axis. That is also the graphical representation of a Boyle's law. Say, you will be given the multiple choice questions, you will be given the different types of graphical representations. And you will be asked, which represents the Boyle's law? Say, all this. So this one, similarly, say P against 1 by V, straight line passing through the origin, or PV is equal to constant. PV is constant at a constant temperature, and therefore PV against P or V, that will be a straight line parallel to the pressure axis or the volume axis. That is also the Boyle's law representation. So we can represent Boyle's law graphically in 3 ways. The Boyle's law can be expressed in 3 ways. One is the graph like this, or a straight line graph that is obtained by plotting 1 by P against 1 by V. Then it is passing through the origin, or you will get PV against P or V. P or V. Then it is again a straight line which is parallel to the pressure or volume axis. And all these three are the graphical representations of a Boyle's law. Now, let me see whether you have followed this or not. So, what is the relation seen in the Boyle's law? Boyle's law gives us a relation between pressure and volume of a gas at constant temperature. A relation between pressure and volume of a definite mass of a gas at constant temperature. And according to Boyle's law, pressure of a definite mass of a gas is inversely proportional to volume at constant temperature. At constant temperature, pressure is inversely proportional to volume, and therefore P proportional to 1 by V at constant temperature T. That is our Boyle's law. From Boyle's law, we can derive say a relation like this, PV is equal to constant. And that is also another form of Boyle's law. Say P proportional to 1 by V at constant T. That is Boyle's law. Or P, PV is equal to constant at a constant temperature. That is also the mathematical formulation of Boyle's law. Now we can represent Boyle's law graphically, for which we have to plot pressure against volume at constant temperature. And that graph, that curve is called an isotherm. So isotherm is a plot of a curve of pressure against volume at constant temperature. You can see an exponential curve. We have seen that. Instead of P against V, we can plot P against 1 by V. 1 by V. Then you will get a straight line passing through the origin. That is also the graphical representation of Evelyn. That is also Evelyn. That is also graphical representation of Boyle's law. Or you can plot PV against pressure or volume. Then you will get a straight line parallel to the pressure or volume axis, and that is also the graphical representation of Boyle's law. We can represent Boyle's law graphically in three ways. Three ways. All these three are the various graphical representations of Boyle's law. Now, let us say the second law, that is the Charles law. Charles, Charles, Charles law, Charles law. Charles law gives the relation between the temperature and volume. Temperature and volume of a gas. We can call it as the temperature volume below. Temperature and volume, relation between temperature and volume at a constant pressure. Temperature and volume, variation of temperature and volume at a constant pressure. According to Charles' law, at constant pressure, say at constant pressure, constant P, the volume of a definite mass of a gas, the volume V of a definite mass, a fixed mass, a definite mass, a fixed mass. So number of moles, that is also fixed. So volume of a definite mass of a gas is directly proportional. Directly, that is the relation. Directly proportional to directly proportional to the absolute temperature. Directly proportional to absolute temperature, capital T. So we can write the Charles law in this way. That is V proportional to T, directly proportional, V proportional to T at constant pressure, at a constant pressure. And that is the mathematical formulation of Charles' law. The volume of a definite mass of a gas is directly proportional to absolute temperature at constant pressure. So keeping the pressure constant, the volume of a fixed mass of a gas is directly proportional to the temperature, or we can write B proportional to T at a constant temperature, and that is the mathematical formulation of a Charles law. From the Charles law, we can write a relation like this. V is equal to constant. The proportional design is removed. Constant into temperature. Or we can write V by T is equal to constant. V by T is equal to constant at a constant pressure. At a constant pressure. If a pressure is constant, V by T of a definite mass of a gas is also a constant. V by T is a constant. So this is Charles law and this is also Charles law. V by T is equal to constant at a constant pressure. Or V proportional to temperature at a constant pressure. That is a Charles law. Now, from V by T is equal to constant, we can derive a relation like this. V1 by T1 is equal to V2 by T2 is equal to T3 by T3, etc., etc. And this is also obtained from the Charles law. V proportional to T at a constant P, Charles law, or V by T is equal to constant at a constant P, Charles law. From that relation, we will get another relation as V1 by T1 is equal to V2 by T2 is equal to V3 by T3 is equal to etc. etc. And these are the volumes and the temperatures at various conditions. You have to keep the pressure a constant. Okay. Now let us see how does the volume change, vary when temperature is increased or decreased. Temperature is increased or decreased by 1 degree. Let us see that. How much volume changes? From Charles' law, it is seen that for 1 degree, say 1 degree rise in temperature, temperature is increased by 1 degree. Increase in temperature, 1 degree rise in temperature. Then the volume is increased by 1 by 273.15 of the volume of the gas at 0 degrees Celsius. So the volume increases, temperature increases, volume increases. So volume increases by 1 by 273.15 increases by 1 by 273.15 of the volume at 0 degree Celsius. 0 degree Celsius. At 0 degree Celsius, the gas will be having a definite volume. It is having a definite volume. Now increase the volume, increase the temperature, increase the temperature. When temperature increased through 1 degree, temperature is increased through 1 degree, then the volume is increased by 1 by 273.15 of the volume at 0 degree Celsius. Say at 0 degree Celsius, let the volume is equal to V. That is equal to V. Then if 1 degree, there is an increase of 1 degree, what will be the new volume? The new volume will be V plus 1 by 273.15 into V, increased by 1 by 273.5 fraction of the volume at 0 degree. The for a rise of 1 degree, for a rise of 1 degree in temperature, the volume is increased by 1 by 273.15, 15 is 15. 273.15 of the volume at 0 degree Celsius. If V is the volume of the gas at 0 degree Celsius, for 1 degree increase, in temperature, the volume is increased by 1 by 273.15 into V. So the new volume will be V plus 1 by 273.15 into V. That is the new volume. If the temperature is increased by 1 degree. Suppose you decrease the volume, the temperature, you decrease the temperature. When the temperature is decreased, the volume is also decreased. Directly proportional. Directly proportional. So when temperature increases, volume increases. When temperature decreases, volume decreases. So let us see the decrease in volume. Decrease in volume. Say for 1 degree decrease, decrease in volume. Temperature, 1 degree is decreased. Then the volume is decreased. Volume is reduced. Volume is reduced. It is decreased. Decreased by 1 by 273.15 of the volume at 0 degree Celsius. 0 degree Celsius. When temperature increases, the volume increases. When temperature decreases, the volume decreases. You see the case of the decrease in temperature. When temperature is decreased by 1 degree, then the volume is decreased by 1 by 273.15 of the volume at 0 degree Celsius. Suppose the volume at 0 degree Celsius, that is equal to V. Now you decrease the volume. You decrease the volume by 1 degree. So 1 degree decrease. 1 degree is decreased. Then what will be the new volume? At a 0 degree, the volume was V. At the 0 degree, the volume was V. Now the temperature is decreased by 1 degree. Then what will be the new volume? There is a decrease of 1 by 273.15 into V. And this is the new volume. The volume is decreased. Suppose the temperature is increased by 2 units, 2 units, then what will be the new volume? Say 2 degree decrease, 2 degree decrease in volume. Then the new volume will be V minus. This is for 1 degree. What is given here is 1 by 273.15. That is for 1 degree. So for 2 degree, it is 2 by 273.15 into V. That is the new volume. The volume is decreased. Do you get me? The volume is decreased. Suppose temperature is decreased by 10 degree. There is a decrease in volume by 10 degree. Then what will be the new volume? The new volume will be V minus 10 by 273.15 into V. That is the new volume. Okay. Now you go on decreasing the temperature. You go on decreasing the temperature. Now the temperature is decreased. Temperature is decreased by 273.15 degree. 273.15 degree. The volume is, temperature is decreased. If 1 degree decrease, it is minus 1. 2 degree decrease, it is minus. We are starting from 0. We are starting from 0. This volume V is the volume at 0 degree Celsius. 0 degree Celsius. So temperature is decreased by 1 degree. That means the new temperature is minus 1 degree Celsius. Minus 1 degree Celsius. 2 degree decrease. Minus 2 degree. Minus 2 degree Celsius. Then decrease in 10 degree. Then it is minus 10 degree Celsius. Now you decrease the temperature by 273.15. So the new temperature will be minus 273.15 degree. Then what will be the new volume? The new volume is equal to V minus 273.15 by 273.15 into V, and this is the new volume. And what is this volume? You calculate? You calculate? What will be the new volume at a minus 273.15 degrees Celsius? What is the new volume?
V minus V.
Sorry?
V minus V.
V
V
minus
minus
V.
V.
V minus V is equal to,
Zero.
come on, ah, that is equal to 0. This is equal to V minus V is equal to 0. The volume reduces to 0. So the gas, if the gas is cooled, the temperature of the gas is decreased by 273.15 degree. That means the temperature is a minus, we are starting from 0, and the temperature is being decreased. So 0, minus 1, minus 2, minus 3, minus 10, minus 200, minus 273.15 degrees Celsius. Minus 273.15 degrees Celsius. At that temperature, what happens to the volume of the gas? The volume of the gas is reduced to 0. At this temperature, the volume of the gas is reduced to 0. And this temperature is called the absolute zero. It is called the absolute zero of temperature. And we can introduce a new scale here, a new scale. And that new scale of temperature, that's called absolute temperature scale or Kelvin scale. Absolute temperature scale or a Kelvin scale. I shall show it again. Say at minus 273.15 degrees Celsius, the volume of a gas is reduced. The gas volume is reduced to 0. Volume of the gas is reduced to 0. And this temperature, that is minus 273.15 degrees Celsius, this one, minus 273.15 degrees Celsius. The various scales are degree Celsius, degree Fahrenheit, and Kelvin. Kelvin. In Kelvin, we will not use the term degree. We will not use the term degree. Celsius, degree Celsius. Fahrenheit, degree Fahrenheit. But Kelvin, simply Kelvin. Capital K, Kelvin. In the first chapter, we have studied temperature. The unit is Kelvin. We have studied that. Capital K, Kelvin. Okay. So the temperature minus 273.15 degrees Celsius, at which the volume of the gas is reduced to 0. That is called absolute zero. That temperature is called absolute zero. Absolute. That is absolute zero temperature. So the question is, what is absolute zero? Absolute zero of temperature. Absolute zero means the temperature at which the volume of the gas is reduced to 0 when the gas is cooled. When the gas is cooled, the volume of the gas is reduced to 0, and that is absolute zero. And the value of absolute zero in degrees Celsius is minus 273.15 degrees Celsius. Minus 273.15 degrees Celsius. From here, a new temperature scale is introduced by Kelvin. It is called the thermodynamic scale. Thermodynamic scale. Or it is also known as the absolute scale of temperature. Absolute scale. Absolute. Absolute scale. Or it is also known as the Kelvin scale. Kelvin. Kelvin scale. In the Kelvin scale, the symbol is capital K. There is no degree. Degree is not shown. Only K is written. Degree Celsius will mark degree. degree. See here there is a degree. Degree is there. But in Kelvin, there is no degree. So a new temperature scale is begun from the absolute zero. Absolute zero of a temperature. Absolute scale, zero is a minus 273.15 degrees Celsius. In the absolute scale or in the Kelvin scale or the thermodynamic scale, zero in the absolute scale, Kelvin scale, zero. That is a zero Kelvin. Zero Kelvin. We will not use a degree. There is no degree. We will not write a degree like this. It is not written. Only it is not written there. Only zero K. Only K is written. So it is the zero, absolute zero means the volume at which the volume of the gas is reduced to temperature, temperature at which the volume of the gas is reduced to zero. That is absolute zero. And it is a zero Kelvin. We write it as zero Kelvin. And to get the temperature on Kelvin scale, what we have to do? The degree Celsius is converted into the absolute scale or Kelvin scale by adding 273.15 with Kelvin temperature. Degree Celsius. With the degree Celsius, you add 273.15 to get the Kelvin temperature. To get Kelvin temperature, the temperature on Kelvin scale, the temperature on absolute scale, what we have to do? So the degree Celsius, you add 273.15. Then you will get the Kelvin equivalent. So the temperature on the Kelvin scale, that is shown by capital T. If there is capital T, that is Kelvin temperature. That is absolute temperature. And how you get the absolute temperature that is obtained? If a degree Celsius is given, degree Celsius, to that you add 273.15. That will give you the absolute temperature or a Kelvin temperature. So much Kelvin. For example, say freezing point of water is equal to 0 degrees Celsius. That we know, 0 degrees Celsius. Now you convert this temperature into the Kelvin scale. Convert this into the Kelvin scale. And what will be the boiling point of freezing point of water on Kelvin scale? That is 0 plus 273.15. So much Kelvin. So that is equal to 273.15 Kelvin. And that is the freezing point of water on Kelvin scale. Degree Celsius, 0 degrees Celsius. And Kelvin scale, 273.15 Kelvin. Similarly, the boiling point of water, boiling point of water, that is equal to 100 degrees Celsius. 100 degrees Celsius. Now you convert this into the Kelvin scale. So what we have to do? 100 plus 273.15. So much Kelvin. And this is equal to 373.15 Kelvin. That is the boiling point of water on the Kelvin scale or the absolute scale. Degree Celsius, 100 degree. And Kelvin scale, 373.15 Kelvin. So we get a new temperature scale. It is known as the Kelvin scale or the absolute scale. It is also known as the thermodynamic scale also. And to convert degree Celsius into the Kelvin temperature, so the degree Celsius, you add 273.15 so that you can convert degree Celsius into the Kelvin scale. So these are the things you have to say from the Charles law. So the Kelvin scale is introduced with the application of the Charles law. Now you plot the, the volume against temperature. Volume is directly proportional to, we have studied. Volume is directly proportional to absolute temperature. We have studied that. So here there is absolute temperature, capital T, Kelvin. Then you will get a volume directly proportional. Volume increases, temperature increases. When temperature increases, volume increases. Then we get a graph like this. And that is the graphical representation of a Charles law. See the temperature here. This is the absolute temperature. Absolute temperature. Instead of that, if you are plotting degrees Celsius, then the graph will be like this. Here we have the volume, and here we have a degree temperature, degree Celsius. Here it is Kelvin. Then the graph will be say like this. The nature of the graph will be like this. You'll get a straight line, but here it is a minus 273.15 degrees Celsius. At the temperature, the volume becomes a zero. The volume of the gas becomes a zero. So this is the nature of the graph obtained. Or you can plot the degree Celsius in another way also. Say it is like this. Here there is a volume, and here you have a say 3 degrees Celsius. You will get a straight line this way, but this is not zero. Here this is zero, but this is minus 273.15 degrees Celsius. Then you get a graph passing through the origin. This is not a zero, zero. Here, this temperature is a minus 273.15. So all these are the various forms of graphical representations of the Charles law. And here we have plotted the volume against temperature at constant pressure. Constant pressure. And this plot, this graph is known as isobar. It is called a isobar. Isobar. So isobar is a plot of volume against temperature at a constant pressure. That's called an isobar. So this is a isobar. Similarly, here also you get isobar. Here also isobar. All these are isobars. But the difference is this. In this graph, we have plotted the absolute temperature, Kelvin temperature, Kelvin temperature. But in the other cases, we have plotted degree Celsius. If this is the origin 0, 0, the origin 0, 0 here, then this is the zero volume minus 273.15 degrees Celsius. Or you can plot this way also, but here the temperature is not 0. Here the temperature is minus 273.15. So here is a difference. See, you compare these two, there will be a difference. If here the temperature is 0, 0 degrees Celsius, 0 degrees Celsius, then the volume 0 will be here at minus 273.15. On the other hand, if you directly plot degree Celsius, here it is passing through this point, and this point is not 0 degree, but it is a minus 273.15 degree. Or you can plot the absolute scale or a Kelvin temperature, then also it is passing through the origin. On all these are the isobars for the gas, a definite mass of the gas. And these are the graphical representations of the Charles law. What's the time? Say what? At what time you have to stop? Next period. Okay. Is it time to stop the class? Eh? Is it? Yes. Okay, let me stop. We'll continue in the next class.